Okay, second video, picking up where we left off. I just did this problem. This was number 21 from this problem set. Oh no, I guess not that problem set. From this problem set over here. Oh boy. And I don't know how big that is. Can y'all see that? Probably you can kinda. I don't think there's anything else in here I'm super stoked to talk about. Maybe something like a 32 sine. Maybe something like a 31. 31 is pretty darn good, actually. Let's talk about 31. Maybe 31 and 32. All right, 31. How do you do it? I hope that you would have noticed that cosecant is, of course, the reciprocal of sine. If you didn't notice that, I think you'd be in a lot of trouble here. Okay, what do you do then? Your first impulse might be to multiply through by sine. Because if you multiply through by sine, it'll distribute onto this term, giving 2 times sine squared x. It'll distribute onto this term and just kind of cancel out, giving us 1. And it'll distribute onto this term, just giving us 0. If you do that, are you in danger of losing any solutions? Are ya? Maybe. Maybe a little bit you are. No, you're not. Because what's the alternative? Let's have this chit chat one more time. The alternative, I guess, is to recognize 1 over sine. Well, that was cosecant. So what if you factored out cosecant? Well, factoring out cosecant would give you 2 sine of x over cosecant of x plus... Well, that's bringing us back to the same place, isn't it? So plus 1 equals 0. You guys probably don't see it yet because this is kind of weird algebra, but sine of x over cosecant of x, that's sine of x over 1 over sine of x, which is a complex fraction. And we clean complex fractions up by multiplying by the reciprocal of the denominator, right? So you'd multiply by sine x over 1, multiply the numerator by sine x over 1. That gets the denominator to cancel. And then the numerator just becomes sine times sine, which is sine squared. So long story short, multiplying through by sine leads us to 2 sine squared plus 1 with no extra factor of cosecant in the front. Factoring out cosecant brings us to the exact same place, where we have 2 sine squared x plus 1, but with an extra factor of cosecant of x in front. But again, the same thing that happened before. This factor, cosecant x equals 0, we saw that only moments ago, and I drew you a little picture. This picture right here, a picture that proves to you that cosecant never equals 0 anyway, right? Cosecant doesn't equal 0. Cosecant lives from 1 up and from -1 down, and 0 is quite obviously in between all those things. So this is actually a little bit of a new situation. It's not that cosecant gives us solutions that are extraneous, it's that it just literally doesn't give us solutions anyway. So having it there is kind of irrelevant because the equation that it generates has no solution. So the only solutions we get are from this factor here. And what that means is it is safe to just multiply through by sine, which is probably what feels easier. It should probably definitely feel easier to just multiply through by sine rather than factor out cosecant. Although factoring out cosecant is technically the safer thing. Anyhow, let me shut up. Do I need to solve this? I don't think I do, but I will. You guys are obviously subtracting 1 dividing by 2 to land on a sine squared x that equals negative a half. Problematic. Because now I would go to take the square root, wouldn't I? And I don't think we've seen this happen before. But if I now take the square root of both sides, then I get sine of x equals plus or minus a thing that's imaginary. Question mark. So it sounds like maybe that doesn't have any solutions either. I'm starting to think that maybe, just maybe, this whole equation just has no solutions. Hold on. Okay, I'm back. Guess what? Here's the graph, and it proves that, yeah, we just have no solution. If you graph 2 sine x plus cosecant x, which I did, you get these funky little, well, they look kind of like teeth, don't they? But these teeth live roughly at, round about 3 and a little bit lower, round about negative 3 and a little bit higher. But they oscillate on those on there. And we're trying to figure out when those little humpy doos equal 0. And it's just like before. Cosecant never equals 0. And cosecant plus 2 sine x doesn't ever equal 0 either. We can see it in the graph. We can see it in the algebra as well. So I'm ready to go ahead and say that as much as this equation looked good, it just doesn't have any solutions. So that's that. This next one is probably a different story. So let's do that. No, it's definitely a different story. Of course it's a different story. Right? It's definitely a different story. So let's do 32. 32 is going to feel a little bit similar because I hope you're going to look at cosecant and say you are 1 over sine of x. And I hope you're going to look at cotangent and say you are cosine of x over sine of x. And I hope you're going to have the bright idea to not multiply through by sine, but factor out, not sine, but factor out 1 over sine. You're actually factoring out cosecant, right? So I'll do it as 1 over sine just so you can kind of follow along, but you'd factor out 1 over sine. And of course, if you factor that out of itself, you get a 1. If you factor 1 over sine out of this, then you pretty clearly just keep the numerator, the cosine part, and it equals 1. So what that means is this guy here is really a cosecant. And again, I don't think you'd have seen it, but if you factor cosecant out, well, yeah, obviously, if you factor cosecant out of cosecant, you get the 1. But would you have noticed that if you factor a cosecant out of a cotangent, you get a cosine? You probably wouldn't see that. But you do see it if you break it down. If you break cotangent down to cosine over sine, then factoring a sine out of the denominator means you're factoring out a cosecant, which leaves you with a sine. So you're here now at a factored form equation. And again, you're left to wonder, hey, do these solutions of cosecant x equals 0, are they real solutions for us? Or is it no solution anyway? Or is it solutions that are extraneous? And, well, just like we saw over here 5 seconds ago, this actually, again, just has no solution. It's not solutions that are extraneous. It's just literally no solution because 0 runs through the middle of all those little uppy, downy humpies. It never equals 0. It only equals 1 to infinity and negative 1 down to negative infinity. So it's no solution, which means all my solutions come from the cosine equation. They come from when cosine equals negative 1, which on the unit circle is only over here. So it's actually just that one position, which is pi. And so what are we doing? All solutions. So x equals pi plus 2 pi k where k is an element of the set of integers. There you go, solved it. So the solution set here at the end, not very interesting, but the algebra at the beginning was interesting. Hopefully you understood that. I think I'm pretty happy now. No, I lied. There's definitely one other thing. Hey, let's backtrack. It was lesson 4. Buried inside of lesson 4 were a couple of quadratic looking ones. So 39 and 41, which were definitely assigned homework problems that you had to do. You are definitely responsible for problems like that. So let me grab 41 and do that one for you. So for 41, this is where I think the u substitutions really make the most sense. Because I don't like looking at this. This looks ugly. But as soon as you replace cosine with a u, you get 2u squared plus 3u plus 1 equals 0. And then you got to factor this. And y'all can factor by grouping if you want to. But I'm just going to do it kind of by guess and check. You want a 2u squared, you're going to need a 2u and a u. You want a 1, you're going to need a 1 and a 1. There's not a hell of a lot of guess and check to do here. It can only be a 1 times 1. And then you want it everything positive, then you need everything positive. This thing actually factors really easily. But anyway, from here, I would substitute the cosines back in at this point probably. This will be 2 cosine plus 1 equals 0. So it's going to be u equals negative a half, which means cosine of x equals negative a half. This guy will be u equals negative 1, so it's cosine of x equals negative 1. So what's happening now on a unit circle? I'm wondering, when does cosine equal negative a half? And of course that's in these two positions that are both 60 degrees. I'm also wondering, when does cosine equal negative 1? And that's only this one position here. So I get these 3 positions that are both kind of off to the left. It's kind of weird. So how do I generate all of these solutions at the same time? Well, you literally cannot. There is no way to model this infinite solution set with only one equation. So you may as well brace yourself for 2. I think your best bet is to try to hit both of these with just one equation, because that's pretty easy. You'll do plus or minus 2 pi over 3. And you'll go ahead and add to that 2 pi k, where k is an element of set of integers. Then you can definitely get all these guys pretty easily. That's pretty obviously pi plus 2 pi k. And that's it. Okay. So quadratics. Make sure you know how to do quadratics too. I just don't want to do this all night, so I'm going to call it a day on solving equations, and then we can backtrack. In lesson 3 was really just a review of evaluating all these expressions, so we can talk about evaluating those expressions one more time. But don't forget that I did say that you do need to refamiliarize yourself with all these graphs. And you don't have to know a ton. You just have to know like their domains and ranges and stuff. And the big thing to remember is when we restricted the domain of sine, we went negative pi over 2 to pi over 2. But really think about what I'm asking you. If I ask you for the domain, like the restricted domain of sine, you give me the negative pi over 2 to pi over 2. But if I ask you for the domain of the inverse function, remember that everything switches. So the domain of the inverse function would be negative 1 to 1, because the domain of the inverse is the range of the original. It's the negative 1 to 1. That would mean that it's the range of inverse sine that is that interval that we've been talking about so much. It's the negative 90 to 90. That's the range of inverse sine. And I know I talked a lot about the modified domain or the restricted domain. But every time I said restricted domain, I was talking about the original function and how the fact that the original function's domain being restricted meant that the inverse function's range was restricted. So just don't get that twisted. If I'm asking for the domain, you better be giving me the y values of the original. And if I ask for the range of the inverse, then you should be giving me the restricted x values of the original. And yeah, you got to know all 6, because I might ask you about inverse sine, I might ask you about inverse cosine, I might ask you about inverse tangent, inverse cotangent, inverse secant, you get it. So know your domain, know your range, know your asymptotes, maybe know your concavity, maybe be able to make a sketch, but don't go nuts on this. It's not a million points, but it's some points. All right, so now let's do these again. I don't think anybody really needs help with the basics. You guys did great on the basics, but let me do a couple and then hop forward to the harder ones, including the challenge and super challenge problems. So for these, like we said, if you're evaluating an inverse sine function, then you're trying to find me an angle, and the angle you're trying to find me is the angle whose y coordinate is a half. And again, of course, as we've talked about so much by now, is there are 2 places that have y coordinates of a half. But because we restricted the domain of original sine, the range of sine inverse or inverse sine is restricted too. It's only those values from negative pi over 2 to pi over 2. So you can't expect the inverse sine function to spit out this angle. That angle does not lie in the right range. The correct angle is only this one here, the one that is called pi over 6. And that's the main thing behind this is, kind of find the correct point, find the possible points on the unit circle, and then pick the best one based on the restricted domain of the original function. All right, so I'll do like a couple more just for the sake. Let's do the bottom row. Who cares? So when does cotangent equal root 3? If you have it memorized, good for you. If you don't have it memorized, then remember, cotangent is x over y. That you should have memorized. And to get root 3, you'd have to have the root 3 over 2 in the numerator and the 1/2 in the denominator. Then the 2's would cancel out, giving root 3. So that means you're looking for the angle that passes through the point whose x coordinate is root 3 over 2. So those are 30-degree reference angles for sure. And cotangent is different from sine and cosine and secant and cosecant because it's not symmetric over x or symmetric over y. It's symmetric over the origin, to where the other correct answer would be 180 degrees later over here in quadrant 3. But we said before, and I don't mind you guys saying it, quadrant 3 is simply never correct. You can just literally ignore it. So that means the only correct answer here is definitely the one from quadrant 1, which is pi over 6. Tangent of 0 you would do similarly. Tangent is y over x, which means it'll only equal 0 when y is 0. And of course on the unit circle, when y is 0, x is 1. So that's this position or this position. But again, tangent doesn't go from 0 to pi, it goes from negative 90 to 90. So only that angle is considered correct. So you better give me 0, not pi, just give me 0 only. I'm not doing any more of these, you guys get it. All right, so the next step up in difficulty was these two-steppers. And without giving too much away, I was told there was one like this. Maybe it's in the homework. Where are you? You. Nobody ever asked me about this, but this one is strangely different from all the others. How's it different? Well, there's a weird 2 right there. And again, maybe I'm not giving you kids enough credit. Maybe you guys looked at this, saw that there was a difference, answered it, got it right, and then didn't need to talk to me about it. But my heart says that just nobody talked to me about it because nobody ever talks to me about anything. But taking a look at that one, it's a little different. But you know what? It's not weird. I mean, you guys get, probably, that you're just going to evaluate that inverse sine expression first, then you're going to multiply by 2, then you're going to evaluate the cosine. So what the hell's going on here? We've got cosine of 2 times whatever the hell the inverse sine of a half is, and the inverse sine of a half is not hard to figure out. It's the angle whose x coordinate is a half. So you should probably have it memorized by now since we've done a bazillion of these, but Pretty sure x is a half here. 60, right? Yeah, so pi over 3. But wait, there's a 2. So the 2 kicks in now. And we're now doing the cosine of 2 pi over 3. So that 2 actually goes burp and pushes us over here. So we're now not evaluating the same blue angle. We're now evaluating this red angle that's in quadrant 2 instead. So now when you go to evaluate cosine, well, you know, whatever. You still get root 3 over 2. But if, wait, super psych? Cosine is the x. I'm being stupid. Which means I've screwed this whole thing up. Right? I screwed the whole thing up. My bad. Why don't I just rewind and pretend like that first bit never happened? Obviously, when you evaluate sine and you're looking for a y that's 1/2, y is 1/2 at the low spot. So that's pi over 3, of course. So that's pi over 3, which means when you multiply by 2, oh my god, I keep getting it wrong. Pi over 6. Sorry. Obviously pi over 6. So pi over 6. So when you double it, you're now doing the cosine of 2 pi over 6, which is really the cosine of pi over 3. So that little 2 there just kind of changes things to where you're not actually evaluating the cosine of that first angle you found. You're actually up here now at pi over 3 evaluating the cosine of that angle, and the cosine of that angle is the x-coordinate of it, so you actually just get 1/2 again. So we had a half, and we're getting a half as an answer, and that's down to the effect of the 2. So I hope I didn't make too much of a mess of that, but if there's an extra number buried inside of these sort of nested trig expressions, then just, well, it's nested. Just work your way from the inside out like you always do. The most inside thing is this 1/2, and I want the inverse sine of that, so get that answer, it's pi over 6. Then double that, then do the cosine of that angle. And I think that's pretty normal. There's not much else here to talk about. Do remember that arc cosine, that's just the alternate notation. That means inverse cosine. If you see arc cosine, that doesn't mean anything different. What else? The challengey problems. So these were the challengey problems. Partially, because you had to actually draw a triangle for these. So these were weird because you're not actually going to get like a real final answer. The best you can do is give an algebraic expression. And the only way to get to the right algebraic expression, I shouldn't say the only way, but the easiest way is probably just to draw a picture of what's going on. And let's do, who cares, 50. If I'm doing 50, then you'd start with the arc cosine part. Cosine is the x coordinate over the radius. So if you're doing the inverse cosine of x, then that's some angle theta. And you know that that angle theta is the angle such that the cosine of theta would be, well, x over r. And since it's x, I guess x is x and r is 1. So you go to draw that. Now cosine being x is positive, so you would draw a quadrant 1 angle. You're expecting cosine to be positive in quadrant 1. And we know that x is just literally x, and the radius is 1. So what's the y value then? Well, we know that x squared plus y squared equals r squared. That's just the Pythagorean theorem. So you plug in x for x. I guess we plug in y for y. And we plug in 1 for r. And 1 squared is 1. But we need to solve for y. Y is the unknown. So subtract. You get y squared equals 1 minus x squared. Then take the square root. You get y equals root 1 minus x squared. And I need you to resist with every fiber of your being. And I see that that's a little low. And I see that this cosine is trying to sneak away. Oh, for God's sakes. Oh my God. Oh my God. Couldn't be worse. Alright, that was worth it. Had to put that back there. God forbid. Alright. I was about to say that I don't know. I was about to say it's pretty darn important that you guys know that if you're doing the square root of like an a squared minus a b squared, you absolutely cannot do the square root of that and the square root of that. Radicals don't break down like that over subtraction. This thing would not become a minus b. That's not a thing. Don't try to do it. This square root of a binomial is just going to stay the square root of a binomial. It does not simplify in any way. So when I say that y is square root of 1 minus x squared, that's it, and it can't be simplified. Oh, by the way, they want us to find... Oh, I knew I was doing something wrong. We're not doing 52, we're doing 50. They want us to now find the cotangent of that angle. So the cotangent of our same angle, theta, by the way, that guy right there is theta. What's my cotangent? Cotangent is cosine over sine, so it's x over y. So it's the same x we already had, and by the way, x is literally just x, but y is this expression we had to figure out. It's 1 minus x squared, square root of that. That's your final answer. That algebraic expression is the answer. Am I doing more of these? All of those should be fine. All of those should be pretty fine. Aha. This one has an M in it. This one has an A in it. So that's probably the worst one. Let's do 41. So 41 is definitely another draw a picture, work the triangle like we just did. And this time it's cosine. Cosine is, of course, x over r. So if I'm drawing a picture of a positive cosine angle, then bzz, that would be my angle theta. And then around comes a circle. And wherever that circle hits the angle, you would drop straight down. There's your triangle. And we're basically handed that the x coordinate is 2a. And we're given that the radius is 5. So based on that, what would the y coordinate be? Well, we just said it'll be 2a squared plus the y coordinate squared equals the radius squared. It's just a squared plus b squared equals c squared. So you do that math and you're going to get 4a squared. That was a big thing people screwed up on the quiz. They thought that 2a squared was 2a squared. But 2a squared is 2a times 2a. Notice there's two 2's there. So yeah, you got to square the 2 and get 4. This is y squared. This is 25. So y squared is going to be 25 minus 4a squared. So I take the square root. And y is going to be the square root of 25 minus 4a squared. And again, no, you cannot reduce that. So finally, if I want the sine of that, well, sine is just y over r. So what's my y value? It's this big ugly expression we just found. So it'll be 25 minus 4a squared, square root of that, all over the radius, which is still 5. But that expression there would be the sine of the inverse cosine of 2a over 5. So that's it for the problems that are like that. And so the last things are the sort of challenge problems. And something like 48 is a challenge problem. Sure, just 48. Okay, so 48 real fast. 48 is a challenging problem because the given angle is not a unit circle value. I can't just evaluate this and then evaluate that because I have no idea what the tangent of 17 pi over 10 is. 17 pi over 10 is some weird angle. I don't know what it is. But here's what I do know. I do know how to draw it. I do know what 17 pi over 10 is on the unit circle, because pi is 10 pi over 10, and 2 pi is 20 pi over 10, and this would be 5 pi over 10, which means if I add another 5 pi over 10 to the 10 pi over 10, this is 15 pi over 10. So guess where 17 pi over 10 is? I bet it's right here. So where is it? It's 2 pi over 10 beyond the y-axis, but that's not what's important at all. The fact that we're 3 pi over 10 shy of the x-axis is really all that matters. We know we're working with a 3 pi over 10 reference angle. Now the question is, I'm in quadrant 2, and I now want the angle whose tangent is the same as the tangent of this angle. So basically it boils down to, do you want an angle that's coterminal with this? Or do you need to take it from the quadrant that it's in, map it into a different quadrant, and then grab an angle that's coterminal with that angle? And because we're after inverse tan has that restricted domain that goes from negative pi over 2 to pi over 2, right? So we're in the correct quadrant for tan. I do want to stay in quadrant 2, but a rotational angle, the blue rotational angle that you see here, that's not the right way to get to the answer of an inverse tangent problem. To get to the answer of an inverse tangent problem, aren't you supposed to rotate this away in the negative direction? So basically, the answer is not the same angle as 17 pi over 10. It's the reference angle of 17 pi over 10, but rotated in the negative direction, and so that's negative 3 pi over 10. That would be the answer to this challenge problem. Got it? I'm not doing it anymore. I'm sick of it. I think I'm done. I think I've covered what I want to cover. Hey, if you have a question, you can type it into the comments. And I'll try to keep an eye on the comments tonight. And I know it's late. It's already 10, so I hope you guys are going to bed soon. But if you have a question at like 11, I'll try to answer it. And then you can go to bed by 11:15. Don't stay up later than that. All right. I hope this was helpful. Hey, if it was helpful, here's something you could do. You could tell me that it was helpful, and you could say thank you. Doesn't sound like much, but you know, it actually does feel good when people say thanks. So I don't know, give it a try. Okay, bye.